So this is our second of 2 lectures in Chapter 13 on radiation exchange between surfaces. So in this chapter we were introduced to the view factor. What's the notation? Fij. So it's the fraction of photons that leave surface I that impinge or strike or hit surface J. There's an analytic equation. Sometimes it's useful, but a lot of times it's not, because it is a double area integral, and it has the cosine of an angle where the direct line for the point of integration between surface I, it's normal, and then that straight line, that's the cosine of that angle I. And then we have the cosine of theta j. That is for the angle with respect to the normal for surface j. You divide by pi and that distance squared, r squared, and you sum over the area I, the area j. Now, to make this complete, you want to divide by the area I here, or you put it over on the left-hand side of the equation with f. Okay, so that's the view factor. There's the equation, very mathematical. What's the interpretation? Fraction of photons that leave I, strike J. Okay. We had 2 rules. We had the summation rule, the sum of the view factors that leave I and go to any and all J. So sum over all J in the enclosure must be 100%. They have to go somewhere. All right. The other rule is the reciprocity. So if photons can leave I and hit J, then probably, or definitely, some photons can leave J and go back and strike I. And so the reciprocity equation is AI Fi to J is equal to AJ Fj back to I. And we use those in a couple cases to calculate view factors for a network or for an enclosure. Then our enclosures can have all surfaces being black bodies, meaning no emissivity, or the emissivity is equal to 1. And we had a resistor concept come up where we had the nodes being EB nodes. Maybe EB1 or EB2 or EB3, whatever our notation is for our surface, for surface 1, surface 2, surface 3. Then over here, it's the black body emissive power. I don't like that term, but that's what the book uses. Black body emissive flux, because it's watts per meter squared. That's the units on this EB. And then what about the resistance? This is a geometrical resistance, RGEOM. That's my notation. And it's 1 over AF. What do you mean 1 over AF? Well, 1 over A1 times F1 to 2, or in general, 1 over AI Fi to J. Funny units, but that resistance has SI units of what? Can you see that? Can you see what the SI units on that resistance are? 1 over meter squared. Really interesting units. But then this gives us the flow, Q1. And then over here, if this is node 1, and then this would be, let's say, Q2 into node 2. For a network, assume all of them are into the network. And then some you're going to compute to be negative, meaning the watts out of the network. Okay. Well, as soon as we have black surfaces in an enclosure and doing exchange, then we move to gray surfaces. Now those gray are diffuse, and there's some assumptions inside the derivation. But what happened is we get an additional resistor, and the resistor is a 1 minus epsilon over epsilon A. So this may be for surface 1, so 1 minus epsilon 1 over epsilon 1 A1. So those emissivities and areas are for that individual surface, 1 or I or J or whatever number notation for that surface. Okay, it doesn't drive it between EB nodes. Yes, one of them is an EB node, EB, but the other is a J node. What is a J? Name of J is radiosity, right. Okay, and so here, since we use 1 as a subscript, I'll continue and put 1 and 1 there. So it has the black body emissive flux, EB1, for surface 1, as well as J1, the radiosity, for surface 1. So that's the resistance. I like to call it a surface resistance for a gray surface. All right, and then the same thing is it goes into the network. So this would be like Q1 coming in to the network. All right, and then I didn't draw it, but you'll have a bunch of resistors out to other J nodes. Maybe this is J for surface 2, J for surface 5, J for surface 6, whatever. You have a network exchange. All right. Well, there's 2 things that we should be familiar with. Radiant shields. So if you wanted to reduce the radiative transfer, often you just introduce a foil with low emissivity inside, and even with the high emissivity, it'll still reduce the radiative exchange. But if it has low emissivity, it's even better at reducing the radiative transfer. It's like insulation, radiative insulation. That's a radiative shield. Okay, so these shields are common in engineering. And then the other is re-radiating surface, and that gave us that simple equation where you can do series and parallel and get one long expression for the net transfer from one surface to the other surface. I think I showed that again today. Well, as soon as you have radiation down, you can couple it with convection and conduction, heat transfer. Just have to be careful. What drives conduction and convection is a difference in the temperature. What drives radiation, a difference in EB, or a difference in the temperature to the 4th power. So you immediately get some nonlinear equations. And you would use a computer program to sort it all out and solve for the roots of coupled system of equations. All right, number of assumptions. One of the biggest assumptions is that you have to be careful anytime you're dealing with solar. So a lot of times they'll give you alpha S for a surface. Alpha S. What is alpha? Absorptivity. It's a solar absorptivity for that surface. And then somebody can say, well, that surface, it has an emissivity, and that emissivity from Kirchhoff's law is equal to the absorptivity from Kirchhoff's law. And maybe this may be down, I don't know, 0.1, and yet the solar absorptivity is 0.3. And a common mistake is they'll assume the solar absorptivity is equal to the absorptivity, assuming radiative exchange maybe in the 300 or 400 Kelvin range, where it's long wavelength radiative exchange, and you get this gray diffuse assumption. Here, just be careful, because when you have the solar load on a surface, it's in a small range of wavelengths, the short wavelengths, right? Do you remember roughly what it's between? Somebody says, you studied radiation heat transfer. What is a solar radiation predominantly between what wavelengths? Well, visible light's between 0.4 and 0.7-ish, somewhere in there. It's a little below 0.4, about 0.2, and a little above 0.7, but 2. So from 0.2 to 2 is pretty much the wavelengths for the solar radiation. Yeah, there's some lower than 0.2, and yes, there's some greater than 2 microns, but it's much different wavelength characteristics than typical engineering application, room temperature, or even 100 degrees C, or 400 Kelvin or something like that. That's why you have to be careful. A lot of times they'll even put the solar absorptivity, divided by the hemispherical emissivity or the hemispherical absorptivity. And if this is a large number, and I showed a table where they put that in the textbook, then especially if you lay something in the sun, it can get very hot compared to another surface with that being closer to 1, and you lay that in the sun and it won't be as hot. It won't get as hot, high temperature. All right. Hopefully a lot of things in this chapter, as well as the whole class, have helped you understand the world we live in better. All right. Well, that's a long chapter. Any comments or questions as we get started? So we have 2 surface enclosures. Both surfaces are black. So you can put a surface like this. You can put another surface like that. So this would be surface 1. And this would be surface 2. And if you were interested in the transfer between them, then you'd probably put out a network. You'd probably put like here, go EB2 and EB1. And we'd have the Q in the 2 and the Q in the 1. And it's really that simple. And what's that resistor? It's a 1 over A1 F1 to 2, which is equivalent to 1 over A2 F2 back to 1 from reciprocity. All right. All right. Somebody says, maybe I'm given this temperature EB1, so I can calculate, given temperature T1, so I could calculate EB1. Or maybe I don't know the temperature 2, but if I could calculate EB2, then I could use it to calculate T2. There's the relationship. So you just have to set up a network like that and be able to solve it for different problems. A lot of times it's like, oh, what is the view factor from 1 to 2 in this case? So if I have an infinitely long conveyor system, it goes into a hot furnace, which is approximated as that half shell on top. So what would be the view factor from 1 to 1? For this configuration, 0. View factor from 1 to 2, 1. Then you have the view factor from 2 back to 1 and the view factor 2 to 2. If this radius right here, let me see if I can draw it like this. Put the radius, here's radius cap R. All right. What would be the view factor 2 back to 1? How would I calculate it? Reciprocity. So you say A2 F2 to 1 is equal to A1 F1 to 2. And we already calculated that one. And so what is A1 equal to? 2R times some infinite length in the third dimension into the paper, into the plane. So that would be 1. And then you divide by the area 2. What would that be? Half of the, if I went all the way around, isn't that 2 pi R times L? But I'm doing a half of 2 pi RL. The halves cancel, the R's cancel, the L's cancel. And so the view factor is going to be 2 over pi. Do you agree? Or not? It's okay. Thumbs up if you agree. Very good. All right. And then how about the view factor 2 to 2? How am I going to calculate that? I'll tell you what. I'm going to ask you to give me view factor 2 to 2. You're going to need your calculator to 3 significant digits. Let's go ahead and calculate the view factor 2 to 2 to 3 significant digits. All right, so let's go ahead and stop it. And we'll show the results. 0.363 is the right answer. One of the things, can a view factor, can any f I to j be greater than 1? Oh, well, there, fine. Make you happy. Can any view factor be greater than 1? No, so 2 of those are ruled out right away. Looks like this is 1 minus something, right? And then 1, no. And so that's the best we can do. How's that? And so the view factor is about 36% of the photons that leave surface 2 impinge back on surface 2. You got this as 1 minus 2 over pi, correct? Great. All right, let's solve this problem. We have a long cylindrical heating element of 20 millimeter diameter. So D up here is 20 millimeters. It's very long. So into the third dimension, you know, it looks like almost it could be a sphere, but it's not. It's a very long cylinder. Okay. And its temperature is 700 Kelvin. It's in a vacuum. When it says vacuum, what do you think that means? Something about natural convection? Negligible. Only radiation. It's located 30 millimeters from an insulated wall of low thermal conductivity. So this is 30 millimeters. It looks like it's from the center of the cylinder to the surface of the material, which is a wall, which is a low thermal conductivity, okay, and it's insulated on the backside. Okay. Assume both the element, that's the heater element, and the wall are black, and the surroundings are at 300 Kelvin. So you might just put an enclosing surface, and that's 300 Kelvin for the enclosing surrounding surface. That's some ceilings, some walls in the room. What is the maximum temperature reached by the wall in Kelvin? So, if you have to read the equation, a question like this, 2 or 3 times before you fully digest it. So let me do this. Ask a question. Where is this temperature going to be observed? Where is its location? Not the magnitude of the temperature, but where is that maximum temperature to be found? And I want to pause, I want to walk around, and I want you to reproduce a sketch, and then I want you to put the tip of your pencil where, or underline or shade or whatever, and show me where that maximum temperature is to be found. So a lot of us said, look, they're interested in the temperature of the wall. The temperature of the wall here is probably going to be different than here, different than here, different than here. Why? Well, way over here, it doesn't have the effect of a 700 Kelvin long cylinder, you know, above it, radiating down to it. So basically, I'd anticipate that's the location where the wall would have the maximum temperature. So out here, I mean, you can march way far away, and guess what the wall temperature is going to be if it's way far over there? 300 Kelvin. It's going to be 300 Kelvin. Okay, so how am I going to calculate that maximum temperature? Should I consider an enclosure, or should I consider the area for the wall to be something like this and calculate the average temperature for that segment? Or should I calculate the temperature for this little segment? Clicker question. No, well, yeah, okay. We'll say that what you want to do is you want to consider a small little section that is directly below the heater element on the wall. And that's where you'd anticipate the maximum temperature. So, this is a tough one. I have a cylinder length L located above the heater elements above the surface, and we know the diameter. If you try to draw that to scale, does this look to scale at all? No, not at all, right? So the diameter, it would be maybe if I busted this length into thirds, 1, 2, 3. That's close enough. And then it would be 10 and 10 for the heater element. The diameter would be 20, 10 and 10. So that's closer to reality, okay? But I have to do this. I have to say what would be a view factor from a small little element to a heater element. I mean, I can pick this one to be surface 1 and that to surface 2, or change it up and put 2 down here and 1 up there. Doesn't really matter in my notation. But what am I going to do here? Let's say this is the diameter 20 millimeter. Let's say that I go down here and I'll say that this is 2 millimeter. 1 on either side of the point of maximum. 1 millimeter on either side. Somebody says I have 2 millimeter down here. I have a 20 millimeter diameter, infinitely long, heater element. The length is 30 millimeter. This is also a strip. Doesn't it also go infinitely deep? Yeah, so I'm calculating the temperature of that strip that goes actually long down with it. So how am I going to get the view factor? Let's call this one surface 2 at the bottom and surface 1 up here. View factor 2 to 1 or 1 to 2, either one. How am I going to get that view factor? I want you to work on it for a minute. This is going to be tough. I'm going to be hard on you today. So let's try this. Let's have you give me a numeric estimate of that view factor. Good, only 2 digits. I mean, if you can get it to 3, whoopee. I mean, you're just way ahead of everybody else. But I want you to use your insights. Now, first of all, if somebody puts in a negative value for this answer on the view factor, guess what? They're wrong. How about they put in a number greater than 1? They're wrong. It can't be. Okay, so positive between 0 and 1, and just eyeball or find an equation or do something but input numeric response for the view factor. Let's go 2 to 1, where 2 is this little strip down here that's 2 millimeters wide, and up here we have a 20 millimeter diameter infinitely long heater element located 30 millimeters above. All right, so input that. That's not the high clicker. All right, well, I'm going to pick it up here. Let's go ahead and take a look at what people inputted, right? You ready? Just one significant digit. I mean, good luck, right? Getting it. So let's take a look at the results. So this is really pretty close. This one's really close. Let me see if anybody else. Did they put these in order for me? 0.3, 0.33. Who got 0.33? Really? Pretty good. So, but this all just guessing. I mean, unless you're a super calculator and you already figured it out, or you solved this as a homework problem due, right? So, but that's pretty good. I'm going to give credit. I'm going to give credit, good credit. Why not? Give credit. Oh, come on. You're testing me there. Oh, no, 38. So no, you can't give credit for 2 nor 38. But the rest we'll just say, good, you tried. What you do is, in the textbook, you can look at the different configurations, and none works perfectly. Probably the best one is a strip like this and then a strip like that, because it's 2D, and then in table 13.1. Or you can do some of the references, and it's really not that hard. You just, in Google, you would just say, I have an infinitely long cylinder over a plate, and can you calculate, give me an equation for that view factor. And so if we find, using the internet, infinitely long cylinder, the illustration calls this surface 1. That's why I wanted to call that one up there surface 1, so it's consistent with the correlation I found. And then below had an infinitely long plate, and it's surface 2, and it's directly, symmetrical, and you have the distance is B right here, and that this distance in the illustration off of the internet is distance A, and the diameter is, well, maybe I copied that illustration incorrectly, but let me show you here. This is what I copied right here. All right, lowercase a, lowercase b. They're doing it from 1 down to 2. But anyway, I calculated F2 to 1, which is using reciprocity. This is the equation for F1 to 2. It uses its inverse tangent of this B parameter, which is B over A. And you can pick and say, okay, I know my diameter D, which is needed in the area of 1. The length L is going to cancel. These two L's cancel. But I pick up the 1 over pi arctan of B over A. Okay, but I have to pick a B. So if I pick a B of 1, that means I have 2, B here, B here. It's like 2, a width of 2. And I use that equation. I calculate the view factor from 2 back to 1 to be 0.333. If I change it, make it smaller, it becomes 0.33333. Guess what the pattern is? It's 1/3. All right, so let's go back to our problem. So for this configuration, itty bitty little strip, 1/3 of the photons that leave surface 2 impinge on surface 1. Where do the 2/3 of them go? To the surroundings. To the surroundings. Okay, now that we have that view factor, 2 to 1 is 1/3. The view factor 2 to 3 is 2/3. This is surface 3 out here. What is the temperature of surface 3? 300 Kelvin, the surroundings. What we want to do is we want to do an energy balance. Energy balance for what? Well, we want to do it for this little surface right below because we're interested in the temperature of that surface. So how much would be conducted from the backside to keep it at the whatever temperature it's going to be at? So it'd be like Q conduction plus Q radiation going from 2 to 1 plus Q radiation going from 2 to 3. That's my energy balance. The sum of the flows, right? But here, what do we know about this wall? It's insulated. It's an insulated wall, so there's no conduction. cooling it off or heating it up. It's nothing. So the energy balance boils down to a radiative transfer from 2 to 1 plus the radiative transfer from 2 to 3 is equal to 0. Where'd you get that equation from, Professor? It's a radiative energy balance. Okay, what's my equation for the radiative exchange going from 2 to 1? Well, it's as easy as A2F 2 to 1 sigma T2 to the 4th minus T1 to the 4th. Does that look familiar? We could use the resistor concept, but this time it may just slow us down to put in resistors. And then what about the radiative transfer from 2 to the surrounding 3? A2F 2 to 3 sigma T2 to the 4th minus T3 to the 4th equal to 0. The way I've drawn it is everything's from 2 somewhere. 2 to 1 and 2 to 3. Professor, I think the high temperature is this one. That's 700 Kelvin. Well, then this whole term is going to be negative. Yeah, so the sign's going to work out. Okay, so we have 700 to the 4th. We have an unknown temperature that we're trying to calculate to the 4th. We have the Stefan-Boltzmann 5.67 times 10. You know what? Doesn't the Stefan-Boltzmann cancel on both sides? Yeah, it does. So let's skip it. Doesn't the area 2 cancel on both sides? Sure. So all you have is you have this fraction 2 to 1. That's a third. And then you head over here, the fraction, I don't know why I changed color to red. Let's leave it 1/3. This is 2/3. T2 to the 4th minus 300 to the 4th. I have one equation, one unknown. What I want you to do is I want you to solve now numerically for T2. And so let's see, if I manipulate this equation, I get that T2 is equal to 1/3 of 700 to the 4th plus 2/3 of 300 to the 4th. I don't know why I put that parenthesis there. Put it. All right. Divided by nothing. Divided by 1. Raised to the 1/4 power. And we get that it's 541, 540, 540. Why do we get so many digits? I should not count those correct. It's too many digits. 540, 540, 540. All right. Well, that's what it is, okay? So 541 is a good number. Any questions about that? How come 3 people got 523? Okay, make sure you can do that on the test, right? Use that 1/4 power and T to the 4th. Okay, that's how you calculate that. Let's press forward. Well, what happens if you have gray surfaces? You could do the same thing. You could still have that enclosure like this. Surface 1 down there, surface 2. And what you would have is you'd have not just EB1, you'd also have EB2, but you'd have J1 and J2. You'd have radiosity nodes. And between the radiosity nodes, you'd have the 1/AF view factor, the geometrical resistance. And then you'd have between the emissive or black body emissive power flux node and the radiosity node, you'd have 1 minus epsilon over epsilon A. And 1 minus epsilon over epsilon A. Those are surface resistances. So this would be for surface 1, the emissivity of 1, and the area size of 1, and emissivity 2 and the area of 2. And this geometrical resistance A1 F1 to 2 or A2 F2 back to 1, either one. I think we did this last time. What happens if surface 2 becomes black? The emissivity is 1 for surface 2. What happens to this resistor? This resistor does what? Goes to 0. Okay, so because the resistor doesn't go to infinity, it goes to 0, these become the same when the emissivity is 1. So you would just get rid of the J1. It's just EB1. You don't need a separate node there. 2 nodes, just collapse to 1 node. All right. You can do a 3-surface enclosure where they're gray. It just becomes tedious. I would encourage you to always just put in Q1 into the node as well as Q2 into the node, into the network. And the sum of all the Q's into the network must equal to 0, so some of them are going to be positive, some negative. You can work out a simple relationship, and you'll see the equation like this in the textbook. Let me just outline it. Here is our sum of 3 resistors in series, geometrical surface, geometrical surface. If the view factor 1 to 2 is 1 and A1 is equal to A2, then you would have like 2 parallel plates in that configuration, right? Not this. This is not where the view factors are 1. Okay. In that case, you can move the A1 up here. Just bring that A1 up because A1 is equal to A2. And then you have 1 minus epsilon over epsilon. That's like 1 over, this gets replaced by 1 over epsilon 1 minus 1. And then that cancels with this one, like that. And then you get a slight reduction, algebraic reduction, and you get this result. You become familiar with the equations. You don't have to memorize them, and it's also in the textbook for the exam if it applies. All right. Here's the equation in the textbook, isn't it? All right. All right. Let's solve this problem. Consider 2 very large parallel plates with diffuse gray surfaces. So here's surface 1, here's surface 2. For the upper plate, the temperature is 975 Kelvin, and the emissivity is 1. Hey, it's black. It's not gray. I mean, it collapses to be black. Okay. And then surface 2 is 500 Kelvin, and the emissivity of 1 is 0.8. First question, what is the radiosity for the upper plate? The second, what is the radiosity for the lower plate? Then what's the irradiation for the upper plate? And then the last question, what's the net radiation exchange between the plates? So let's do this. Calculate the radiosity for the upper plate. What symbol would that be? Is that J for the upper plate, surface 1? Is that what they're asking us to calculate, J1? Okay. Let me do this. I want you to work on this and input a numeric response. But let's agree on the units for J1 first. The units of J1, should that be watts? I want you to do a clicker, answer A if you think it is. Watts per meter, answer B. Watts per meter squared, answer C. Watts per meter cubed, answer D. Or I don't know, answer E. And let's take a look. And we only have one outlier, straggler. It's watts per meter squared. It's a flux, basically, watts per meter squared. So that's our answer. Let's get rid of all this. You already know the answer? Okay, so this is in watts per meter squared. So now let's go ahead and change it to numeric response. And go ahead and calculate J1. You don't need to set up a radiative network. You can calculate it. So let me talk about this a little bit. If you wanted to, you would set up a big radiative network. Hey, that's what we just solved for. We'd have the EB1, we'd have the J1, we'd have the J2, and then the EB2. And those would be our four nodes, 2 radiosity, 2 emissive fluxes. And then what do we have? We have our resistors, resistors, resistors. We just talked about this 1 minus epsilon over epsilon A. And if the emissivity of 1, surface 1 is 1, what happens to this resistor? It goes to 0. What is the difference between EB1 and J1? 0. They're the same. They collapse. So EB1 is equal to J1. That's how you calculate J1. So with that hint, let me give you a few more seconds. You can pick up right now, or you can pick it up anytime. So what do we get? 51239. Perfect. Okay, excessive. This is good. This is okay. This is good. 5-1. I don't know why some of these all are messed up. 512. I'll give it credit. But you're going to want to save. Hold it. That's too many digits. You're off by a factor of 10. Right? 51239. Not an extra 0 there. But I'll give you credit. All right. 51,240 or 51239. All right. Now, what the next one is, what's the radiosity for the lower plate? Let me back up a little bit. There's another way to think about calculating this J1. You can put the network together like that, but you can think about this. Here comes in G1, and then 1 minus the emissivity, that's the reflectivity, times G1, that's the reflected component, plus the emissivity EB1, that's all J1, isn't it? So J1 is equal to 1 minus emissivity of G1 plus the emissivity EB1. You can think about that equation. Emissivity of the surface is 1. Hence, this becomes 0. That's just 1. It's just EB1. You get the same result. EB1 is equal to J1. But sometimes it's helpful to think about this. You know, how do I calculate J1 or how do I calculate J2? Because right here, what is the radiosity for the lower plate? I want to calculate J2, don't I? How would I calculate J2? Maybe I take 1 minus the emissivity 2. So J2, isn't that equal to 1 minus emissivity 2 times what's coming in the surface 2? If it's coming in from surface 2, where's it coming from? It's only coming from 1. So this right here is J1 plus the emissivity 2 times EB2. So you can kind of go back to this illustration, the basics, to calculate J2. Let me let you calculate J2 and input it in the numeric digit, but you're going to put in a number that's 5. All right, so J1 is equal to, or G1 is equal to J1, which is 51239. You put in the 0.8, you put in the 0.8, and then this is sigma 500 to the 4th. You add it all up, and we got 1308. Oh, it's close enough. Close enough. Is that right? That's close enough. I guess I'll give this credit. Too many digits there. What do you think? Good enough. Anybody else? All right. Okay, irradiation for the upper plate. Well, just like So G2 is equal to J1, you're right. Now, if we take a look at it for part C, the G1 is equal to what's coming off of the lower plate, J2, which we just calculated. So the irradiation, what's impinging on the upper plate, is what was outgoing from the lower plate, which is, so guess what that is? Same numeric value. What is the net radiation exchange between the plates? And we want it in watts per meter squared area of the plates. Okay? So let me let you struggle with that. Input a response. All right, so let's go ahead and stop it then. And there's a couple ways to do it. You can come back to this illustration if it helps you organize. And what you have is you have the flow from 1, because it is warmer, all the way through. So what's the flow through this resistor, where we know the J1 already we calculated 51240 watts per meter squared. The J2, 13080 watts per meter squared. What's this resistance? 1 minus epsilon, not epsilon, sorry, 1 over AF, 1 over AF. So if we pick an area, a lot of times I just like pick the area equal to 1 meter squared, then we remember, hey, everything is per meter squared. And what's the view factor from 1 to 2? Is that the same as 2 back to 1? Is it just 100%? So guess what that resistor is? 1. If you want to use the units, 1 over meter squared, you know. So what's the flow through this when I have a potential and a potential known and a resistor of 1? The flow is the difference in the potentials divided by the resistance divided by 1. So just like somebody said, this Q double prime, because it's a per unit area, is just going to be the J1 minus the J2. Yeah, so we'll go ahead and look at that. 38160, 38160, 38. No, I'm just going to give these credit. I don't know what happened here, but let's stop. Okay? Look good? Okay. Re-radiating surface, we covered this last time. When you have a re-radiating surface, that then collapses, knocks out. You have series, then combine in parallel, then in series again, and you get a nice long equation for the flow from the hot surface, accounting for what re-radiates to the colder surface. The direct transfer as well as the re-radiating part. All right. Okay. Solve this problem. The end of a cylindrical liquid cryogenic propellant tank. So here's my tank. Looks like it's insulated. Looks like this end is at T1. Okay, or T of tank. That's not T1. That's temperature subscript T for tank. Okay. It looks like it has an emissivity of the tank at that surface. Has a radiant shield, and that shield has some temperature Ts for the shield. And on both sides it has an emissivity 1 on, let's say, the right side, emissivity 2 on the left side. Okay. It's protected from external solar radiation by placing a thin metallic shield. We just talked about that in front of the tank. Assuming a view factor F from the tank to the shield, between the tank and the shield is unity, is 100%. All surfaces are diffuse and gray. Hey, that's this whole chapter. Okay, if you have anything other than diffuse gray, well, then go back to the previous chapter and consider orientation and angles, etc. The surroundings are at 0 Kelvin, so we put everything in a huge surroundings at 0 Kelvin. Given that the temperature of the tank is 100 Kelvin, the emissivity on both sides of the shield is 0.05. The emissivity of the tank is 0.10, and the solar irradiation is 1050 watts per meter squared. So this is that solar irradiation, and the magnitude is given 1050 watts per meter squared. Find the temperature of the shield, Ts, and then what is that heat flux to the end of the tank. How would we begin? First of all, you would reread that problem statement 3 or 4 times to digest everything that's given in it. All right. And then what I would do is I need to calculate the temperature of the shield, right? So I would put together a radiative network. And in that radiative network, I would have J nodes and EB nodes. And I can't spell nodes, N-O-D-E-S. All right, those are my 2 types of nodes, my J nodes and EB nodes. Next, I'd have 2 types of resistors. I'd have my geometrical resistor, my 1 over AF, and I'd have my surface resistors, which are 1 minus epsilon over epsilon A. Do me a favor. You know this is a temperature given. This is a temperature given. This is the temperature of the surroundings. SURR is equal to 0 Kelvin. So 3 temperatures we're talking about. I want you to give me a network, a radiative network for this problem. Sketch it out. That's the first thing. I'll walk around and check it. You only have 2 types of resistors and 2 types. So this was the hardest part of the problem, is setting up. And so what I would do is I would maybe try to say right here, I'm going to have an EB of the tank. And because I have some emissivity of the tank that's different than 1, I'm going to come off and I'm going to have J of the tank. And then I look at what I have over here. I have a shield. Well, okay. But I don't go exactly right to EB of the shield. No, no, no. I have to have the EB of the shield, and then I have J of the shield side 2, or J2, but I emphasize it's the shield second side radiosity. All right. And then likewise I have J shield side 1. And then it's a little tricky, but I'm going out to space, and that surrounding, J of the surrounding is equal to EB of the surrounding, because anytime you have a very large surroundings, it's like effectively black. All right. And because we know the temperature is 0 Kelvin, it goes to 0 watts per meter squared. It's really a good ground. It'll take as much heat you dump to outer space, and it won't increase the temperature of outer space. It'll stay at that effective 0 Kelvin. And so we have that last resistor. So let's go ahead and put our values in. This would be a 1 minus epsilon tank over the epsilon tank area of the tank. This would be the area of the tank view factor tank to shield. This would be 1 minus the emissivity 2 over emissivity 2 area of the shield. 1 minus emissivity 1 over emissivity 1 area of the shield. 1 over the area of the shield view factor shield out to surroundings. All right. So I like to put in a Q right in here, even though it may be negative. I like to put Q tank, and then here, even though it's going to be definitely negative, Q surroundings from the ends. Okay, now, do you like the network so far? Any questions about it? That's a hard thing to do. I mean, I could have given you this network and then, but if you have to develop your own network, like you probably have to on the exam, it has to be right and it has to make sense. Okay? Probably a lot of mistakes are made in this EB of the shield, and then you have the J on this side and J on that side, the radiosities of the shield. They're different. Okay. Okay, now we finally are going to handle this solar irradiation. So sometimes it helps if we just pick sort of the area of the tank is equal to area of the shield is just 1 meter squared. It helps us conceptually, I think, figure out the problem. And so I have the solar irradiation. It's coming and bombarding somewhere. Okay, how do I stick it into this network? Where do I plug it in? I could plug it in here, here, here. Well, that's not, I got to put it into a node. Here, here, here. I mean, there's 1, 2, 3, 4, 5, 6 options of where I'm going to put some sort of solar load into this network. And then conceptually, what's going to happen is once the solar loads into the network, it's going to either add the heat to the tank or add the heat back out to the surroundings, isn't it? So where do I put that solar load? Do I put it in location A, B, C, D, E, or F? Multiple choice, go for it. And let's take a look at what we said. Yeah, some of us are lost a little bit. Okay, I'm going to give credit for D and E. Do this. I said D and E, not F. Get rid of this. Get rid of these two. Get rid of that. All right. How much gets into and absorbed into the shield surface? Isn't it going to be a fraction of G sub S? And what is that fraction of G sub S? It's going to be the shield's solar absorptivity. So alpha S. I know I could put SS. It's the shield's solar absorptivity. Let's just call it alpha of the shield. Do they give us a solar absorptivity for this problem? No. If you had to guess one, what would you guess? It would be the shield emissivity. A guess would be the absorptivity of the solar absorptivity of the shield would be epsilon 1 from Kirchhoff's law. So basically 1/20th of the load would be absorbed. Where would 19/20ths be? Where would the 95% go? Be reflected. And so here you could put 1 minus alpha S times G sub S. Doesn't that add to the outgoing? All right. Now we're interested in what is the load into the tank. Well, first of all, we need to calculate the temperature of the shield. All right. That was for part A. How do you calculate the temperature of the shield? If I know EB of the shield, isn't that sigma T shield to the 4th power? Yeah? How are we going to calculate it? Well, pick an area of the tank, area of the shield to be 1 meter squared. Otherwise, you're working with per unit area all the time. And so this would be the 1 minus the emissivity of 0.1 divided by 0.1 times the 1 meter squared. That's 0.9 divided by 0.1. Isn't that 9? Units of inverse meter squared. I'm going to leave off the inverse meter squared. Okay, what does this resistor boil down to? The area of the tank is 1, the view factor is 1, it's 1. What does this resistor here boil down to? This one is 1 minus the emissivity 0.05 divided by 0.05 times the 1. Right? So this is 95 over 0.05. Is that 19? 19? So I have these resistors in series. So I can sum them to get an equivalent resistance of 29. Inverse meter, if you'd like to put the units. All right, let's take a look on the outside right out here. I have this node right here. And it gets a little tricky because this adds to the J, the radiosity outgoing from the load, but because this JS1 and EB1, you can just, I hate to say it, but neglect this term. So I only have a load going into EB of the shield, which is alpha the solar absorptivity times G sub S, which we can calculate. This was 0.05, this is 1050, so give me the magnitude of what goes into this right here. 0.05 times 1050. Somebody want to run that for me? 52.5. So that's watts per meter squared. We're going to pick an area of 1 meter squared, so that's how many watts. 52.5 actually get absorbed into the shield. Now, it can be re-radiated out toward the surroundings. And so if I do this, what's that resistor right here? It's 19, isn't it? And then what's this resistor's value right there? 1. So this is 20. All right. So it's like I have a resistor to a node, a resistor to another node. This is 0. This is EB of the shield. This is EB of the tank. I can put my sigma, my tank temperature is, was that part of the problem? The tank temperature is 100 Kelvin, right? It's right here, 100 Kelvin. So that's calculatable. This is calculated. We want to calculate EB of the shield. I want you to calculate EB of the shield. I have a resistor. I have a resistor. The values are 20, 29. The potential over here is sigma times 100 to the 4th power. The potential over here is 0. What is EB of the shield? Can you calculate that for me? And then once you get that, that's sigma T shield to the 4th. Then to get the temperature of the shield, it's EB of the shield divided by sigma to the 1/4 power. But calculate that first, EB of the shield. And we'll go ahead and let numeric response. And to help you out, let me do this. I forgot to put in here what that flow is. We just calculated it. It's 52.5, right? 52.5 goes in. So do an energy balance for this node. So 52.5 watts going in is equal to what flows out that way, which would be EB shield minus EB tank divided by the sum of the resistances 29, plus what flows out that way, which is EB shield minus 0 divided by the resistance of 20. So algebraically, this is 52.5 equal to 1 over 29 plus 1 over 20 times EB shield, and then put over, well, minus EB tank divided by 29. So EB shield is equal to 52.5 plus EB tank divided by 29 divided by 1 over 29 plus 1 over 20. So let's go ahead and take a look at what people are inputting for their answer. As you add your answer, I'll be able to see it. I like the 623. Those that got 174 redo. 623. I like that. I like the 623.74. How many people have calculated the EB of the tank, which is sigma T of the tank to the fourth, which comes out to 5.67? Yep, it comes out to 5.67 to help you a little bit. Well, in the interest of time, let me stop. Hey, are we over time? Crap. I've got to stop this. Sorry about that. I'm going to just give everybody select all. Good job. Graded. All right. So that allows us to calculate EB of the shield. Then you calculate the temperature of the shield. You come up here, the temperature of the shield is 324 Kelvin. What's the next part? What's the heat flux? Well, since you calculated this and you know the resistances, you just go back and say, what is the amount that went toward the tank? What is the amount that went toward the tank? You picked an area of 1. So basically, that's trivial. Getting the temperature of the tank is hard. And you find that 21.3 watts per meter squared. All right. Thank you very much for your attention. I'm out of time. Remember that for the next test, it'll be around 8 problems, and this is how I'm going to pick the problems. Get good night's sleep before the test. What time are we going to start? 7 a.m.? I'll see you Wednesday, 7 a.m. Thank you for your attention.